Module 4, Lesson 7, Replacing Letters with Numbers. So looking at our learning targets here, we are looking at representing real-life situations with mathematical expressions, and we are also looking at experimentation using expressions and comparisons. We're also going to look a little bit at the idea of things that can vary or change. I-can statements for the lesson. Show and explain that a letter, which is a variable, represents one number in an expression. Show and explain that expressions have letters in them are called algebraic expressions. So when we start to throw in variables, we're switching from numerical to algebraic. Show and explain that when a number replaces a letter in an expression, the expression can be evaluated to one number. So when we plug in numbers for those variables, we can then have a numerical expression. So take a look at this first example here. What is the length of one side of this square? So we've got 1, 2, 3 units, and it's a square, so all 4 sides will have the same number of units on them. So if we want to find the area of the square, what formula would we use? And this is kind of a blast from your past, things that hopefully you have learned before. Hopefully you remember that area is the number of squares in a figure, and the squares of course are all the same size. And hopefully you remember that the formula for the area of a square is the sides squared. So hopefully you remember that you would take the 3 units and multiply it by the 3 units to indicate that there are 9 squares in this square. And notice we designate this as square units. There's a whole big long discussion to be had about whether or not you would say units squared. That can cause some confusion. I like to emphasize that what is normally used is we say square and then the units. So on this first model, it would be really easy to count the squares. 9 of them, no big deal. What about on this second model? Is it practical? Does it make sense to draw or count all of the squares? Notice that this square has a side length of 23 centimeters. So stop and think, do you want to draw all of this out and count all of this to find the area? My head says, boy, that's a lot of little squares to draw and count, and if I make a mistake, hard to catch. So what expression could we write or build to find the square's area? Well, we just reviewed that we find the area of a square by squaring the sides. So 23 squared. And our units would be centimeters. So 23 centimeters times 23 centimeters. So we would multiply 23 times 23 to find the area. And we should find out that there are 529 square centimeters. And this is where sometimes things get a little bit sideways. If we read this left to right, we would see centimeters squared. But I'd like to continue to emphasize that we would actually read this as square centimeters. It's not technically wrong to say centimeters squared, but it can cause a little bit of confusion. Thinking back to the lesson that we did on exponents, do you mean, when you say centimeters squared, do you mean this or do you mean this? So in other words, do we find the number of centimeters and then square it, or is that the number of squares? We keep that very clean and unconfusing by saying square centimeters. If you were to say to me 9 centimeters squared, in my head I could think of 9 centimeters, and then I would square it and I would get 81. That's a little bit different than 9 square centimeters. All right, so what formula for area did we use to find the area of the first two models? Well, we did area is equal to the side squared, or area is equal to the side times the side. All we've done is taken this exponential form and written it out in expanded form. So let's stop and think about what do each of the variables in the formula represent. A formula is kind of a canned expression, an expression that is used frequently over and over again that is accepted. Well, S is the length of the sides. And I'd like to point out that S is a variable, and so the length of the side of the squares can change. We could have a square that's got 3 units on a side, a square that's got 9 units on a side, a square that's got 55 units on a side, a square that's got 4.5 units on a side. The big letter A is frequently used to denote the area, or to say this is the area. Now the area is going to vary depending on the length of the side. So the length of the side is going to decide what is the area. So in the formula, area is equal to side times side. Is it possible for the first S to have one value and the second S to have a second value? Could I say that the first S is going to be 3 and the second S is going to be 4? Stop and think about that for a minute. Does that make sense if we're talking about a square? Hopefully your brain said to you, no, that does not make sense when we're talking about squares, because squares have all 4 sides the same length. To extend that, when we talk about formulas, the letter, the variable, represents one number. So in a formula, the variable S can only stand for one number. So if I say that S is going to be equal to 5, S has to be 5 every time in that formula, every time in that expression. I can't have one of the S's being 3 and another S being 4. S is a value. It represents one number. So in the first model we looked at, S was equal to 3. In the second model, S represented 23. The A was represented by a 9. That was the area. The A was represented by 529. That was the area. Each of these is one number. So got some squares here. Need to point out these drawings are not to scale. Obviously, this right here is not 25 inches. So we're going to complete the table, organize our work and information in the table here. Length of one side of the square. Looking at this first one here, the length is 4. And we don't know what we're measuring in, so we would call it units. The square's area would be, so the area would be equal to the sides squared, and we know that the side is equal to 4, so 4 squared. And it does say expression, so I'm going to get rid of the A equals here. So we could have 4 squared, or we could have 4 times 4. And then the square's area written as a number. So 4 squared would be 16, and square units. Like to pay attention to those labels as much as we can. All right, looking at the second one, it is 25, and we know the unit we're measuring in now. It's inches. And the area is 25 times 25, or 25 squared. And just as a point of interest here, I can point out that it is 25 inches times 25 inches. Now, if we multiply inches times inches, then we wind up with square inches. Repeated multiplication straight out of the exponents lesson there. So 25 times 25 is going to give us 625 square inches. All right, let's take a look at a second example. We're going to move away from squares and look at rectangles. The formula for a rectangle is the area is equal to the length times the width. It's a nice, easy way to find the area of a rectangle. And we don't have to count the squares when we have the formula, things that I appreciate. So what does the letter B represent in this blue rectangle? What is the B standing for? Well, the B is obviously one of the sides, but because we know about rectangles, we know that this side is equal to this side. So we would say that the B is equal to 8. One value. Now, we're going to be given some information here. The second rectangle is divided into 4 equal parts. They are specifying that these 4 pieces are equal. So what does the number x represent? Well, I know that each piece equals 4, and I know that x is equal to 2 of the pieces. So x is equal to 2 times 4. 2 pieces here. Looking at a little bit of tape diagram, 1 piece here, and x is twice as much. So x is equal to 8, and we do have a unit there, 8 centimeters. Now stop and think, how did you arrive at this answer? I've already kind of talked through mine. I said, well, this is 1 width, and this is 2 widths. So x will be twice as much as 4. So the total length of the second rectangle, well, this is 1 piece, and the total width is 4 times as much. So I could do 4 plus x plus 4 more, which would be 4 plus 8 plus 4. Or I could say that I'm going to do 4 times 4 because there's 4 pieces. But in the end, I'm going to find out that it's 16 centimeters. Lots of different ways to think about this. So now we're going to be given another piece of information. These 2 rectangles have the same length and the same width. And we need to find the area of each rectangle. Well, I know that the width here, well, let me step back here. The area is equal to the length times the width. I know that the width of the 2 is going to be 8, so I will substitute that in. I know the length is going to be 16 because we just figured that out. So the area is going to be equal to the length times the width, 16 times 8. And 16 times 8 would give us 128. And we need to pause here and ask, what are our units? Well, we were measuring in centimeters, so we could say square centimeters. So have a brief discussion with your neighbor. How can the formulas, or talk with yourself, talk with a parent, how the formulas for the area of squares and rectangles can be used to evaluate area for a particular figure, meaning finding the area. Now hopefully your discussion will center around, we have information that we can substitute in to an expression. I can substitute the length for L, I can substitute the width for W, then I can multiply. So the area of a rectangle square equal to length times width. Substitute the value of the length for the variable and the value of the width for the variable, then I can multiply to find the value of A. So let's take a moment here and look at another exercise. So we need to find information about these 2 rectangles. First question is, what is the length? 1, 2, 3, 4, 5, 6, 7. 7, and it looks like we're looking at units. It doesn't specify anything for us. The width, 1, 2, 3, 4, 4 units. And if I write that as an expression, I've got 7 units times 4 units. I'll abbreviate units as UN. And then I can multiply and find that I have 28 square units. Second one here, I've got a length of 46 meters. I've got a width of 32 meters. As an expression, I've got 46 meters times 32 meters. Notice we're working with the formula here, length times width. So I am substituting the length in for L, the width in for the W. And then we could go ahead and we could multiply that out and find 1,472 square meters. All right, so we've looked at a couple of two-dimensional objects. Now we're going to look at a three-dimensional object. Three-dimensional objects have three ways to measure them. We have the length, the width, and the height. We're looking particularly at some rectangular prisms. And they have given us a formula here, multiply the length times the width times the height. And because there are three things that we are going to consider for volume, we will have cubic units, so raised to the third power. So what does the letter L represent in the first diagram? Well, that represents the length. And the W represents the width. And the H represents the height. Since we know that the formula to find the volume is length times width times height, what number can we substitute for the L in the formula? Well, here's a length, here's a length. So we could substitute in a 6. So what other number could we substitute for the length? There is no other number. Only one number can replace one letter. I can't say that the length is going to be 6 and 2 and 8. That doesn't work. So what number can I substitute for the W? Well, substitute the 2. So the length is connected to the length, the width is connected to the width, and of course then what can we substitute for the H? The H will be connected to the 8, the height. So the volume of this second rectangular prism, well, 6 times 2 times 8. So the volume is equal to the length times the width times the height. 6 times 2 times 8, which would give us 96 centimeters times centimeters, which gives us cubic centimeters. 96 cubic centimeters is the volume. All right, taking a look at another exercise here. The length of the rectangular prism is 12 units. The width is 5 units. The height is 15 units. And I've got 12 units times 5 units times 15 units, which is going to give us a reasonably sized number here, 900. And I've got units times units times units, which will give me cubic units. Looking at the second rectangular prism, now, it gets a little tricky here because, which one's the length, which one's the height? It's a rectangular prism. There are 3 dimensions. I can say this is the length, this is the width, this is the height. As long as I'm not substituting 2 different numbers in for the same variable, I'm okay. So I can have 23 centimeters, I can have 4 centimeters, I can have 7 centimeters. I've got 23 times 4 times 7. And I know that these are going to be cubic centimeters. And when I'm done multiplying, I should have 644 cubic centimeters. So, quick closing questions here. So how many numbers are represented by one letter in an expression? 1. 1. If I've got S plus S plus S plus S plus S, I can't have this one being 1 and this one being 3 and this one being 5 and this one being 3.5 and this one being 8. I can't do that. In this expression, S has to be one number. 1. And when that number replaces the letter, so in other words, when we have substituted numbers in for the variables, the expression will be evaluated to one number. When we substitute in those numbers, the expression changes from algebraic to numerical. So, quick lesson summary here. Variables. Variables are symbols like letters, and they are placeholders for a number. They stand for where we're going to put a number. Expressions. Expressions, we have numerical expressions. And we also have algebraic expressions. Numerical expressions simplify to be one number. Algebraic expressions have the variables in them. So there's two ways to build expressions. We can start out with the numerical expression and replace some of the numbers with letters. So here's an expression, and we have substituted variables in. Another way we can build it is to build it as an algebraic expression, and then we can substitute values in to get the numerical expression. All right, so hopefully at this point you can show and explain that a letter, a variable, represents one number in an expression. Hopefully you can talk about expressions that have letters in them and call them algebraic expressions. And hopefully that you can explain that when a number has replaced a letter in an expression, once we've done that substitution, we can evaluate that. We've switched from an algebraic to a numerical expression. All right, so we are chugging along on our learning target. So once again, we're making some progress in real-life situations. Finding area is a real-life thing. Finding volume is a real-life thing. Using formulas, being able to substitute values into formulas and simplifying them. Very much a real-life experience. Talked about varying here. We haven't done comparison yet, but we're starting to look at situations where values will vary. Did a little bit of experimenting with formulas today. Areas of squares, for example. We had side squared, and we found the area for a variety of values. 2, 3, 8, for example. And we looked and said, what happens when the value varies? So that concludes Module 4, Lesson 7. If you've got any further questions, make sure you talk to your teacher. Make sure that you do your practice problem set.